start out with a few questions. And so a lot of them are already pre-folded, and the answers are either A, B, C, or D. And, whatever answer you think you want to go with, you can just fold it. And so, for example, if you want to go with A, exactly, a cheap clicker version with no record whatsoever. So you just fold it and hold up, whatever letter you want to answer. Okay, so who thinks there are less than 10 known planets in the solar system? Who thinks there are less than 10 known planets in this solar system? How many planets are in the solar system that we know of? The usual suspects: Mercury, Venus, Mars, Earth, Jupiter, Saturn, Neptune, Uranus, and, of course, well, that's why I'm saying 10 or less. It is categorized as a dwarf planet. It's not considered a classical planet anymore, but that's a whole different talk. Okay, the next question, just for yes or no. Who thinks these are the only known planets in the universe? Nobody. That's a good sign. Let's see, nobody in the live audience. Let's see how many people we have online. Yeah, for our second question, these are definitely not the only known planets in the universe, because, we go from solar system, like now we're considering all the other stars in the universe, if they have planets around them. Okay, it's the third question. Who thinks there are less than 10 known planets that orbit a star other than the sun? So how many of those planets that orbit other stars do you think we know of? Is it less than 10?
In the universe?
Yeah. That we know of already. Yeah. Including outside, yeah. Any not including the planets in the solar system for right now. We know, of those. But what about outside the solar system that are orbiting stars other than the sun? How many do we know? Less than 10? No, good thing, because nobody agrees, because who thinks there are more than 100 planets that we know of that orbit a star other than the sun? Okay, now would be a good time to agree. Yeah, we know about 406 other planets that orbit stars other than the sun. And when I went to high school, that was like totally out of the picture. No one would have even thought, well, of course, scientists, but, regular people wouldn't have even thought that there might be other planets orbiting stars other than the sun. So this is a really exciting subject. And of course, with that comes up, there are 10 to the 11 stars in our Milky Way. So that's like 100 billion stars. And there are even more galaxies out there, like the Milky Way. Of course, there are other types too. But with each also 10 to the whatever stars. So there's a huge amount of stars in the universe. What's the probability that there might be one that has a planet with liquid water? It might be higher than zero. So that's sort of a very exciting prospect. And that's sort of what this talk is based on. But before we go out into beyond the solar system, well, what about our own solar system? We don't just have the planets, but then among the moons, the larger moons that are orbiting some of the planets, there might be conditions for liquid water. So in essence now, the first thing we're going to do is, okay, let's stay local. We're looking at life similar to us based on water, and then first see what we can get in our own solar system. Okay, and now we have a couple of questions. Okay, here's the first question. Deprived of which item below would you die within a few weeks? What do you think? In the room here, we have mostly A's and C's. So it's sort of, there's one person with B. So it's sort of split half and half. So between A and C, well, What do you think? If you think of going a day without food, well, you could do it. I mean, you might be grumpy at the end. And I mean, there are a lot of cultures that actually have fasts where they go, without food for a day and then, eat at night or something like that. And, they've survived hundreds of years. What about water? You need water. And you need water a lot sooner than you need food. Just try to go a half a day without any liquids. I mean, that also means, no fruits or vegetables with a lot of liquids. And, I mean, you'll definitely feel it. You'll feel it. You'd be a lot more than grumpy. Deprived of this, you would die in a few days. That's essentially what we just talked about. Okay, so let's preview the results. And we have mostly C's in the room and 100% C's online. Okay, now obviously that leaves just one more question here. What about the air? Deprived of this, you would die in a few minutes. Well, that's sort of an experiment that you could try out. But luckily, if you hold your breath and faint, then your body would start taking over and breathe again. So you'd make it maybe a minute or two tops before you'd become unconscious. This is about planet atmospheres. So essentially our first inclination is we look for life like we know it here on Earth. Which of the planets, and that's why I put them in quotation marks, as you can see in some of the choices here, have no atmosphere? Okay, so it's split up. Most people answer C. And I mean, with atmosphere, some B's. I also see a lot of B's. Some people are changing their minds now. With atmosphere, I really mean, gas surrounding the planet. Okay, let's see what we have online. 100% Mercury, Pluto, the moon have no atmosphere. And that's pretty much correct. Okay, that's why I put them in quotation marks. Quotation marks. The moon is a terrestrial object in the sense, that it is rocky, it has a surface, and it has gravity, that people can bounce around on it. And in fact, there are moons that orbit other planets that are larger than our moon. In fact, Jupiter has a couple of moons that are larger than the planet Mercury. So those moons in their own right, if they happen to have formed closer to the sun, they would orbit the sun, and we would consider them planets. So, the definition of planet is sort of a little bit variable. The definition that we live by now, that has been handed down since 2006, that may not be the end of all definitions. It could be reclassified at some point in the future. So that's why I have the quotation marks. Let's go to the next question. So which of these planetary objects, I just didn't want to clutter up the screen too much, have a very thick layer of atmosphere? Let's see. Here in the room we say thick atmosphere, lots of gas. C. Yes, definitely what we call, and it's again in quotation marks, the gas giants. So, and online we have, it's almost an even split, but 57% is still the majority for C, the gas giants. Because sometimes you think of the gas giants, sort of like a thick outer gas layer, and you wouldn't necessarily call it atmosphere. Some people would say outer gas layer, so, the wording can be a little bit misleading. Okay, let's go to the next question. Which planets have a relatively thin layer of atmosphere? Okay, now, the only choice that's left at this point, of course, is A, Earth, Venus, and Mars. And I don't know if you've talked about Venus. I know in my online class we've been dealing with Venus for a little bit. And compared to Earth's atmosphere, if you just could, it's similar in the sense that, you have a gas layer, and then you have a rocky surface. So there's a distinct, here's the gas, here's the rocky surface that objects can walk on, land on, something like that. Venus has a significantly thicker atmosphere than Earth, but it is still terrestrial in the sense that there's this distinct boundary between a gas layer that thins out near the top and then a rocky surface. Whereas the gas giants, they have a very, very thick layer of gas, and then if you go towards the center of the planet, that sort of gets compressed into something that feels like a liquid further down. So you wouldn't say it that way. Okay, let's go to the next question. Planet sizes. Which planet below is medium-sized? Or actually, I forgot the plural and the quotation marks. Sorry about that. So which of the planets below is medium-sized, half to twice Earth's diameter? What choice would that be? Yeah, it's a range. It goes from a little bit smaller than Earth to a little bit larger than Earth. While you're thinking, let's see what our online people say. Yeah, 57% Earth, Venus, Mars. That's the range. Mars is about half the size of the radius of Earth, and of course up to twice, so that's the Earth's range. Yeah, so for the people in the room, no, the choice would be C. That's the range that Earth is in. Smaller, on the smaller end, it would be half the Earth's diameter, and then including the Earth all the way up to twice the Earth's diameter. So that's the size range that the Earth would be in. Okay, let's go to the next choice, the next slide. Which planet below is large-sized, meaning over 3 times the Earth's diameter? Over 3 times. Okay, so that's clearly, very clearly, okay, here in the room, it's A, the Jupiter, Saturn, Neptune choice. And online, it would be C, and 100% got that. Very good. And then, of course, the last question is the remaining choice. Which planet is small-sized, less than 1/3 of the Earth's diameter? So that would be choice B. Okay, well, enough with words. Let's look at a couple of numbers. Okay, I'll give you a moment to look at these choices here. A, we have 464 to 470. B, negative 133 to 27. C, 50 to 70. D, negative 163 to 427. And E, 0 to 100. So the question is, what is the percent of our bodies that is water? Yeah, it's pretty clearly. I think you got a good grasp on that. So here in the classroom, C, and also 80% of you folks online answered C. So that's very good. Now, all these temperatures are in Celsius. What is the temperature range of Venus in Celsius? I know my online, at least those online people of mine in 1010, they've been dealing with Venus, so I hope we get some good answers there. See, how about the classroom here? Yeah, I do see a lot of correct answers. It's A, 464 to 470. So that's the surface temperature of Venus in Celsius. And why that is the case is a whole other lecture. What is the range of liquid water in Celsius? Yes, E would be the correct answer. 0 degrees, water freezes. 100 degrees, it boils, and that's here at sea level on Earth. Let's think about Mercury. What's the temperature range on Mercury? Okay, well, we knew Venus is always hot. Yeah, Mercury, part of it should be hot, but all of it all the time? Okay, what about Mars? Take a look at the answer. So Mars, okay, mostly B, couple of C's, okay, looks very good. And then online also we have mostly B, so that's very good. Yes, Mars can get very, very cold. It's further away from the sun, but also it does not have a lot of atmosphere. It has some atmosphere, but not a whole lot. So, whatever is on the night side cools out pretty quickly. Whatever is near the poles is very cold. But on the day side, along the equator, it can get above freezing. 27 degrees is a little bit warmer than room temperature. So that would be Mars. Okay, and this is the last question. What grade level do you think these questions were written for? Okay, let's see. I see lots of A's, and yeah, also online we got lots of A's. That's right, they were written with 5th to 8th grade. So that answers your question about the Celsius scale. Well, nowadays, this was written in the, I think 2004 or 2006. So, if you've already gone through elementary school earlier or middle school, then don't worry about it. I don't know if they already taught you Celsius back then. So this is the title screen. I put a couple of links here. I don't know how many of you are familiar with Pink Floyd. I know it's a testament to our age. But yeah, when I was in my teens, Pink Floyd was really huge in Europe. So they made a little song, Is There Anybody Out There? And when I started to think about this talk, this is sort of the first thing I thought about. Now, I'm going to post a link to the PowerPoint and everything, so you can actually go and get to that link. Or you can go to YouTube and go to Australian Pink Floyd. Don't ask me why Australian, but Australian Pink Floyd. And then is there anybody out there? We did the questions, and so first we're going to look at, is there possibly extraterrestrial life in our solar system? Well, quick question, what do you think? Have we found any evidence, any strong evidence for life on other bodies in the solar system other than the Earth?
Yes.
So you raise your hand if you agree. Yeah, that there is. So, yeah, people online, give a check if they agree that there is strong evidence for life. That's scientific evidence, I have to point out. We're talking about science. So there's strong scientific evidence for life in our solar system other than on Earth. And, okay, here's the answer. No, we have no strong, unambiguous evidence for life on any other object in the solar system other than the Earth. Well, we have, evidence that there was liquid water on Mars in its past, and we're going to talk about that. So let's go to our solar system. Well, look for liquid water. We looked at the temperature range on Mars, and in fact, mostly frozen, but it still gets a little bit above freezing. So right now, the conditions are not right for liquid water to be able to be maintained on the surface. There might be some gullies where some subsurface water might get heated during the day and then gushes out, but the air is so thin, the air pressure is so thin that it immediately boils away and evaporates in the atmosphere. Well, there's another very interesting object, and that is Jupiter's moon Europa. And this moon is larger than the Earth's moon, and it turns out it's covered with an ice layer. Now, we don't know enough yet, but we think that, well, obviously there are cracks in the ice layer, so it must be shifting around. There might be the possibility that there's liquid water underneath. So whenever we think liquid water, we get excited. That might be life as we know it. Here are pictures. If we go to the next slide, and we look at pictures of dried up river valleys, this looks pretty familiar. Well, actually, this here, the Ares Vallis on Mars looks sort of familiar. We could see something like that on Earth. Or the Nigel Vallis, I don't vouch for my pronunciation of these things. Or if you look at the picture up top on the upper right with the crater, what does this look like, these scalloped edges there? Does it look like the crater formed when the surface was dry or when it was wet? When it was wet, yeah, you could try that. Throw a rock really hard into a mud puddle. That's sort of what that looks like. So we have evidence that Mars used to have a much warmer climate in the past where it could sustain liquid water on the surface. So that's already a very strong ingredient that we need for life as we know it. And that's also why we're so interested in this planet and have so many rovers roving around and trying to find more evidence, like organic molecules or fossils or something. Okay, then here about Europa. It's far from the sun, but then it's in orbit around Jupiter, which is the largest planet of our solar system. So that means there are actually tidal forces, just like there are tidal forces that the moon exerts on Earth and Earth exerts on the moon. There are also tidal forces that Jupiter exerts on Titan, and Titan exerts on Jupiter, except Titan is much smaller than Jupiter, so you see much more of an effect. And the inside, you can think of it like a racquetball that is repeatedly being hit. So that's what the tidal forces do. So there's some energy coming in. So it's considered to be heated by tides. And this is sort of the next slide, an artist's rendition of what a future mission to Europa could look like. So what we see, those alien spaceships here, or that's us. I don't know if you've seen Planet 51. We are the ones that are actually going out into the solar system and sort of invading other planets and objects. But this is sort of an artist's rendition. They would design like a lander that would punch through the ice and then release like a submarine of some sort, some sort of a probe that would go around and look for life, measure the water chemistry, the temperatures, map the terrain. And I hope I'm going to be still alive when a mission like that takes off. So we haven't seen anything yet, but stay tuned. This is certainly an exciting time to be alive for astronomy. Okay, so there are possibilities in our solar system. We haven't found life yet, but we sort of have conditions here and there that would allow present life or maybe life in the past. But of course, now that we've discovered 406 and counting other planets orbiting other stars, well, let's take a look. What can we find out about those? So, there's a new term here. It's called exoplanet. And this is, you'll probably see that a lot, if you keep up with astronomy news, whenever there's a breakthrough or anything. So exoplanet is probably the term that they'll be using, an abbreviation for a planet that orbits a star other than the sun. Why did it take so long? I mean, we've been studying the sky with telescopes since when? Yeah, Galileo, 16 something. So why only now at the end of the 20th century? I think it's 1996 when the first exoplanet was discovered. Why did it take all the way until now to actually discover a planet orbiting a star other than the sun? Well, if you remember how large, if we just look at the proportions of our solar system, how large the sun is compared to, let's say, if Jupiter were the size of a soccer ball, how large do you think the sun would be? Like this, my outstretched arms? Like the size of this large lecture hall, and maybe even larger. So stars are huge. And what is another important difference between stars and planets? Big ball of glowing gas. Stars produce energy, and lots of it. So they're like the floodlight in a football stadium. And what about planets? Do they produce a lot visible light? I mean, why do we see them at all? Yeah, they reflect the light of the star that they orbit. So that's how we can see all the other planets and the moon in the solar system. So planets orbiting other stars are extremely hard to find. I mean, the thing is, the other stars are very, 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 very far away. So in fact, they're so far away that even the closest star we only see as a point of light. So even if we look through the most powerful telescope we have, still all we see is a point of light. So how are we supposed to find a planet that's orbiting it? Well, I'm going to skip over the first methods that were used. There's sort of like a gravitational tug that made the star wobble a little bit, and there's a Doppler shift. So maybe all these terms may ring a bell. But let's focus on, for the sake of time, the most recent methods that we're using. So there's one method that's called the transit method, and that's sort of like, if you imagine a fruit fly flying in front of the lights of a car, the high beams of a car. So that's sort of it. The star would be the high beam of a car, and then the fruit fly would pass in front of it. And if we measure the brightness of light that we get from the high beam fruit fly combination, or mosquito, if you don't like fruit flies, go with mosquito, something tiny. If you follow along the light curve in position 1, the planet has not covered up the star at all, so all we're seeing is starlight. So it's the regular, unadulterated starlight. Well, once the planet starts passing in front of the star, well, there's like a little dark spot in front of the star that is blocking out a tiny little bit of its light. So this is now position 2, where the light curve drops. And actually, how quickly it drops is also going to be important for what type of planet it is. But then while the planet is passing in front of the star, we see the star just a tiny little bit dimmer. And it's sort of like, just about on the order of 1%, or, well, in the single percents. So you wouldn't even be able to tell it with your naked eye. And then, of course, once the planet has passed the star, the brightness goes back up to the original brightness. So I was already mentioning that over 400 exoplanets have been found. And of course, the first planets we find are the large ones. The large Jupiter, larger than Jupiter planets have been, that orbit very close to their star. Those were the first ones detected. So those are 257 of them. They're easy to find because they're large. 0 Earth planets, Earth-sized planets, have been discovered yet, because they're very tiny. And just to show you how tiny, here's a side-by-side impression of the sun with a Jupiter transit. So that's sort of the size relationship of what it would look like on the left, where you see the sun and then Jupiter blocking out a little bit of the sunlight. And then here on the right, you see what it would look like if Earth were to pass in front of the sun and would block out sunlight. So you can tell, that's like you need much more sensitive, meaning much more expensive and advanced equipment to detect an Earth-sized planet passing in front of the sun, or an Earth-sized planet passing in front of a star. And we're getting to that point. We're just now getting to that point. Well, just very quickly, if you look at the light curve, how can you tell the difference between a Jupiter-type planet, which is a gas giant, or an Earth-type planet, which has basically an insignificant atmosphere, that's, and then like rocky surface, dense rock. So it's a very sharp edge. Whereas a Jupiter-type planet, it's a gas giant, so, it starts, it's not as sharp of an edge when it enters, the face of the star that is passing in front of. So you can tell by the sharpness of the edge how quickly the curve dips down, whether you're dealing with a Jupiter-type or an Earth-type planet. Okay, well, this is one space telescope, the Spitzer Space Telescope, that is put in space, and it is there since 2003. It sees infrared light. Now, why is that an advantage? It's an advantage because in the infrared, many planets may not emit or reflect a lot of light in the visible, but when you go to infrared, they do emit their own, well, infrared, what kind of radiation is that? Heat. So it's a sort of heat radiation. It's kind of like our bodies. We see our bodies with visible light because, it reflects the light from the light sources around it. But, when you get close to your skin, you can feel the heat coming off of your skin. So with an infrared camera, and you can go to this website here, Caltech's Infrared Zoo Gallery, just to show you what animals would look like in the infrared. Unfortunately, I can't pull that link up for the people here online. Maybe I can just very quickly take a look at just one image. So I'm clicking on this link. And see see what we'd like to see. How about the hound dog? Okay, so you see the visible image in the visible light on top, and then on the bottom, you see the image of the hound dog in the infrared. Okay, and now the people in the room here have to tell us, what does the infrared image of the hound dog look like? Like, I mean, can you see the color of its fur? No. You see lots of colors, but what do the colors correlate to? Temperatures. For example, the nose of the dog. Yeah, that's a color that, well, these are false colors, of course, but yeah, it shows the dog's nose is cold. And we all know why, right? And, well, what about the eyes? They're very hot. And then, depending on where blood vessels are closer to the skin, that's the part that shows up in a hotter, warmer color, and so on. Yeah, let's go back to the PowerPoint. So it turns out, if you see the image here on the bottom, the left image shows a star and a planet. It's an artist's conception, but still in the visible. So the planet is very faint, hardly to pick up. On the right side, we see the star and the planet in infrared. Because the planet does have some surface temperature of its own, it's emitting some heat radiation of its own. So it's brighter, relatively brighter in the infrared. Okay, then if we go to the next the next slide. This is an image where instead of looking at the light curve of the star, you take a spectrum. So, while the planet is not passing in front of the star, you can see the starlight just by itself. And then when the, oh, wait a minute. Sorry, my brain is getting a little bit frazzled here. The very left image on the top here, okay, they're side by side. You get a combined spectrum. So you get the spectrum of the starlight, with all the spectral lines and, temperature of the star. And in addition to that, you also get, a very faint planetary spectrum, because the planet is also giving off a little bit of infrared, but then the reflected radiation and so on. So once the star, this is now the picture here in the middle, once the planet passes behind the star, you get the spectrum of the star all by itself, because the planet's light is blocked out. So that means you can actually subtract the two, and the very faint difference, the very dim difference, is the spectrum of the planet by itself. Whenever we take a spectrum with spectral lines, what can we tell? That's now for the 1020 people. What can we tell by the spectral lines of an object? Yeah, here's a rumbling. I think you're coming to the right conclusion there. Yeah, what the object is made of. What kind of molecules or atoms are there. So, we can, for example, figure out with some of these hot Jupiters that we've discovered by this technique that they must be hotter than 1,000 degrees. Their air is hot enough. There are some spectral lines that indicate there's rock vapor, so silicates. So there could be a weather forecast on some of these things of, well, tomorrow it'll be cloudy with a chance of rocks. That you have precipitation in the form of rocks. That's how hot it is there. So here's the next one. This telescope is fairly new, put into space. It started May 12th, 2009. And so far it's gone through a lot of tests. Planets that were already discovered, it sort of checked to see if it came up with the same results, to see if it's working. And, what the Kepler uses the transit method that we talked about earlier. So, okay, we have the star, and when the planet passes in front, it dims for a little bit, that type of method. And so it can tell what size the planet is, by the amount that the starlight dims. It can get the orbit size, it can get the temperature. And of course, once we know the orbit size, we can tell if the planet is in the habitable zone for that star. Now, what's the habitable zone? based on the questions we went through earlier, what does it mean, the habitable zone? Yes, where water remains liquid, so where life like we know it could exist. Okay, this is just a quick slide. So Kepler looks into the constellation of Cygnus. So it only scans a very small area in the sky. Okay, here are 3 different types of stars. And you can see, well, the top image is that of a hot blue star. The middle image is that of a yellow star. And the bottom image is that of a cool red star. Now, which type is the sun? Yeah, it's sort of like the middle. Yeah, we're like, it's like the 3 bears and Goldilocks. You know, we have the perfect setting here. We just want to make sure that we don't mess it up. So anyway, if you look at, hot stars, obviously they're really, really hot. So you have to go further away from the star so that the temperatures are cool enough, for liquid water to exist. But because they're so hot, that range extends a little bit. So it starts further out and then it extends a little bit wider. And well, we know our sun-like stars, but if we look at the cooler stars, they're sort of like really dim. They don't emit a lot of energy. So the habitable zone is really close to the star, and it's not very wide. So chances of finding one with a planet in that thin distance range are lower, because, it has to be much more of a coincidence. Okay, if we go to the next slide, well, what are the best stars? Do we want to live around a cool red star? I don't know if you remember, let's see, Mercury's orbit. Mercury's orbit around the sun. What's going on with that? Or the moon's orbit around the Earth. What's going on with that? There's something special going on. It has to do with tidal forces. What is that? Yeah, it doesn't orbit as quick, and the reason is it's tidally locked. The reason is, okay, we have the moon being fairly close to Earth, and of course Mercury is really close to the sun. So there are large tidal forces that early on, while the object was still forming, has locked the smaller object in position so that in case of the moon, the same face of the moon always faces us. So, and with Mercury, it's a 2 to 3, two revolutions for every 3 rotations. So it's a little bit more complicated, but it is a ratio that always stays the same, and it's a fairly slow rotation. That would be a disadvantage for us. A slow rotation, like if we look at the daytime temperatures of Mercury, they're really hot. Nighttime temperatures really cold. And also, well, those of you who take 1010, what does Earth's rotation in combination with its electrically conducting outer core doing? What are we so lucky to have, without which life would probably not be possible? Okay, electrically conducting core and rapidly spinning planet. Sort of rapidly. Magnetic field, yes, the Earth's magnetic field. And this magnetic field is actually shielding us from charged particles that are emitted by the sun, and that would be very damaging if they would hit, life on Earth. If you orbit a cool red dwarf, then you wouldn't have a magnetic field. Okay, what about a hot blue star? Would it be good to orbit a hot blue star? Okay, now the 1020 people are called on again. In terms of the lifespan of a hot blue star compared with that of the sun or cool dwarf. Yeah, I mean, they're like the SUVs. They have a lot of gas, but they burn it at a high temperature and go through it very quickly. So the hot blue stars, they may live hundreds of millions of years, but I don't think they get a whole lot into the billions. And if we think about, well, this is now going into geology, but how long ago did life start on Earth, roughly, just with the simplest microbes? Yeah, billions. I mean, Earth has been around about 4.5 billion years, but then it took another 2 2 billion years until life started to develop here on Earth. So a hot blue giant, well, it might be great, but there's no chance or very little chance that life would have a chance to even emerge before the star. What does a hot blue giant do at the end of its life? Blow up, supernova, neutron star, black hole. Well, no planet in orbit would ever survive that. So, the Goldilocks planet or star and planet combination would be a star like the sun. So it's just right. Lives long enough, and we're far enough away so that we can have a magnetic field protecting us. So then there's another thing. If we look at these spectra from planets, we might find traces of oxygen in the spectrum, or carbon dioxide, or maybe other molecules that are related to life here on Earth, for example. But that still doesn't mean that there is life. It could be life, but we would not be able to distinguish, is it a civilization with intelligent beings, or is it microbes? Our cyanobacteria, when they started up here on Earth, they made oxygen and all that. So just because we see oxygen doesn't necessarily mean that there is an advanced civilization. And also, there could be other non-living sources of these gases. So, before we jump to any conclusions, that's what scientists absolutely do not want to do, we need to run a lot of tests. For the sake of time, let me just sort of skip through this slide. It's just kind of a simulation of what another solar system might look like. So the gas giants may not have to be all the way out there. Another interesting thing to think about is, okay, we've looked at life like we know it. So we're not coming to new boundaries in space, but we're also reaching new frontiers here on Earth. How many of you have heard about extremophiles, or like archaeobacteria, or bacteria that live under conditions that that we could not live under? If we look on Earth here, for example, in that set of 4 images near the top, the bottom left one, with the fire symbol, that's actually a black smoker. That is a vent deep, deep down, several miles down in the sea, so there's no daylight. So no photosynthesis, nothing, no sunlight whatsoever, but there is a lot of energy coming out of a geothermal vent. And a lot of chemicals. And of course, whenever you have energy, like heat, or you have chemicals, whenever you can siphon energy from somewhere to power your metabolism, there might be a living being that does that can live off of that. So, and then of course, we find bacteria in Antarctica, where it's very dry, bone dry, or it's frozen most of the time, or we find bacteria in very acidic environments, and we're just discovering these now. And of course the question is, those are pretty extreme conditions, so you don't need liquid water all the time. Or here, for example, in a mine in South Africa, they even found bacteria that live off of radioactivity. How freaky is that? Or I think the image here, the yellow image here on the bottom right, they live off of metal, corroding metal or something like that. So there's some sort of chemical energy. So wherever there's an energy source that can be harvested, no matter how weird the conditions, there could be life. Back to our solar system, I don't know if you've seen the news about Titan. This is Saturn's moon. It's Saturn's largest moon. And among all the moons in the solar system, this is the moon with the densest atmosphere. In fact, I think the atmosphere might even be a little bit denser than on Earth. And the moon is actually larger than the planet Mercury. So, what's going on with Titan? And we have a probe there, Cassini, which studied the rings of Saturn, but it's also imaging Titan. So it's a very intriguing place. Now, it's far away from the sun, and the temperatures are downright frigid. It's like negative 179 degrees Celsius. So is there any liquid water? No, no way. Any life can develop that we know of? No way. But however, people think, or scientists think, that this might be sort of like the primordial atmosphere that Earth started out with. There's lots of nitrogen, then there's methane and other hydrocarbons. What do we use here hydrocarbons on Earth for? A couple of times a week in order to get us around. Gasoline. So this moon is basically covered in gasoline-type molecules. And are those pleasant? I mean, whenever we go to the gas station, do we just take a ladle and ladle it into our gas tank, or what? Yeah, it's flammable, and then it's toxic. If we inhale it, there can be really bad reactions with our lung tissue, or brain cells dying from fumes. Yeah, that type of thing. So this is sort of like a very toxic environment for us. But being hydrocarbons and being at a very low temperature, some people have theorized for a long time, we're carbon-based life forms. Carbon combining with hydrogen and oxygen, things like that, forming carbohydrates, all these nice macromolecules. And while silicon is in the same chemical column, okay, it has the same number of electrons in orbit. So, theoretically, it could be just as versatile, forming just as versatile bonds than carbon. Now, here on Earth, the conditions are very warm. So the compounds that silicon can form, they don't tend to be stable. But in conditions on Titan, people think, hey, those temperatures are much lower, and in combination with the hydrocarbons, maybe there's some sort of life form that is based on silicon. The thing is, we would not even recognize it if we saw it at first glance, because it's not like us, not at all like us. And of course, by the same token, if we would visit Titan, we couldn't live there, and the metabolic products of those potential silicon denizens, they would be poisonous to us. They might emit something like hydrogen sulfide. That's sewer gas. So stinky, noxious. Well, what about if those life forms came to our planet? It's 100 degrees hotter. So, whoever's made out of silicon might spontaneously combust. Their blood would start to boil. Methane, when you have methane here on Earth, in what form? Is it solid, liquid, or gas? Gas. It's our natural gas. So the blood would boil, and, they might even explode like that. So, life, we have to start thinking outside the box, and, possibilities may open up.